Welcome to The Explainer. Today, we're diving into something super fascinating, demystifying 3D coordinate transformations. If you've ever found yourself wondering how that crazy complex math scribbled down in a notebook actually becomes the functional working code that keeps game characters from, say, glitching straight through the floor, or lets a camera smoothly pan around a 3D animation, well, you're absolutely in the right place. We're going to build a direct bridge today, right between theoretical mathematics and practical C programming. Just think about it for a second. How do game engines, or architectural software, or even wild physics simulations actually comprehend the 3D universe? I mean, they don't have eyes, right? They don't just intuitively grasp depth or volume like we do. Literally everything they know about spatial geometry has to be explicitly calculated. So that incredibly complex software rendering those hyper-realistic worlds is, at its core, just gracefully translated mathematics. So here's our roadmap for this explainer. 1. Mapping 3D space. 2. Cylindrical coordinate math. 3. Spherical coordinate math. 4. Coding cylindrical conversions. 5. Coding spherical conversions. And finally, number 6, the universal space translator. Let's just jump right in. All right, section 1, mapping 3D space. This is our absolute foundation. Okay, so we're essentially looking at 3 distinct spatial languages used to describe the exact same geometric point. It's kind of like a translation guide. In the rectangular or standard Cartesian system, we navigate using 3 straight lines, x, y, and z. Simple enough, right? But when we shift gears into the cylindrical system, we completely change our vocabulary. We swap to a radius r and angle phi, but we actually keep the vertical z the exact same. And finally, in the spherical or polar system, we go all out. We use the vector's total length, paired with 2 totally different angles, theta and phi. The wild thing is, they all point to the exact same spot in the universe, just using completely different instructions to get you there. So the really crucial point here is understanding these 2 angles, which we've pulled straight from the source notes. The angle of azimuth, represented by the Greek letter phi, is our horizontal angle. Imagine you're standing flat on the ground, and you just turn your entire body left or right. That physical rotation, that's phi. Then there's the angle of altitude, theta, which is our vertical angle. Imagine you're looking straight ahead, and then you tilt your head up to spot a bird, or tilt it down to look at your shoes. That vertical tilt is theta. These 2 angles, honestly, they're the fundamental keys that unlock both our cylindrical and spherical systems. Moving on to section 2, cylindrical coordinate math. This is where we start modifying x and y. These hand-drawn diagrams brilliantly illustrate the core concept. Notice how the cylindrical approach fundamentally modifies our standard x and y plane. So instead of just plotting an x-coordinate and a y-coordinate on a flat grid, we project a radius outward, that's our r, and we sweep it across the horizontal plane by our azimuth angle phi. Meanwhile, the vertical distance z remains perfectly straight, exactly like it acts in standard rectangular coordinates. To put it in perspective, it's a lot like trying to find a specific nutritional fact on the label of a perfectly round soup can. All right, section 3, spherical coordinate math. We're leveling up to spheres now. It is honestly so fascinating to see the raw trigonometry doing the heavy lifting here. We're looking at exactly how a sphere's total radius, the magnitude of the vector, which is denoted by those parallel bars around the v, interacts with our 2 angles, theta and phi. By just taking the sine and cosine of these angles, we can mathematically project lines all the way across the spatial axes. Notice how the z-axis is determined simply by multiplying the vector magnitude by the cosine of our altitude angle. It's just elegant, pure mathematics. But okay, what if we actually need to translate between these advanced systems? Well, these handwritten formulas provide the exact bridge required to move from a cylinder directly to a sphere. To find the total spherical radius, we essentially run the Pythagorean theorem using our cylindrical data. You just calculate the square root of r squared plus z squared. It's a neat little trick. Now for section 4, coding cylindrical conversions. This is where math officially becomes code. Let's build into our first major aha moment of the explainer. Notice the logic in this C function for converting spherical coordinates to cylindrical ones. The code, where the cylinder's r is set to the sphere's r times the sine of theta, that perfectly mirrors the handwritten trigonometric derivations we just reviewed. The mathematical theory wasn't just some abstract concept floating in the ether. It is literally the exact blueprint for the application logic. Pretty cool, right? This breakdown really shows the bidirectional nature of these systems. First, the code calculates standard rectangular x, y, and z coordinates straight from a cylinder's radius and horizontal angle. Then we flip it and look at the inverse logic, retrieving cylindrical data back from a standard 3D vector. The program cleverly projects the 3D radius onto the XY plane using the sine of our polar theta angle to find the cylindrical r. It's perfectly symmetrical logic. Section 5, Coding Spherical Conversions. Get ready, because this is the most complex language of the bunch. Remember those handwritten Cartesian derivation notes from a few minutes ago? Connect those directly to these lines of code. This right here is exactly how a machine visualizes a sphere. The program determines the x, y, and z outputs by dynamically multiplying the polar radius by the sine and cosine of our theta and phi angles. When you get right down to it, it is quite literally just typed out trigonometry ready to be instantly executed by a processor. And you've got to love how expertly the C code handles moving from cylindrical back to spherical. The application utilizes standard programming functions, specifically the square root and power functions, to execute that exact Pythagorean formula we discussed earlier, locking in the sphere's radius. Then it pulls out the arctangent function to dynamically calculate the specific trajectory angles based on the heights and radii. It's doing all that heavy lifting for us. Finally, Section 6, the Universal Space Translator, or bringing it all together into a unified, powerful tool. I actually like to think of this specific function as the ultimate Rosetta Stone for spatial translation. It takes completely raw three-dimensional space, just your standard raw x, y, and z inputs, and synthesizes everything we've learned so far. It calculates the base vector length, computes the xy plane projection, and then uses those arctangent functions to elegantly extract our azimuth and altitude. Literally, with this single block of code, the computer fully grasps its exact orientation in a three-dimensional universe. It's a real game changer. So we've gone all the way from scribbles in a notebook to a robust, functioning engine capable of understanding depth, rotation, and spatial relationships. The math is just a set of rules, sure, but the code is the engine that actually enforces them. So the question I want to leave you with today is this. Now that you have the tools to literally translate and manipulate the very fabric of 3D space, what kind of world will you build with it? Thanks so much for joining me on this explainer, and keep learning.